The idea of energy is one that pervades all of our science and indeed our society. Um, Energy itself is a very, very familiar word, but I'm troubled because I think that as ubiquitous as this term energy might be, very, very few actually understand what it means and what it is. I recall once being in a conversation with a fool who was spouting on about some such. The details don't matter, but at some point he said this, that, and the other, and the energy. And I stopped him and I said, wait a second now. What do you mean energy? And his response to me was, you know, energy. And I said, no, I don't know what you mean by that. Can you please be explicit? Because his argument had already disintegrated and fallen apart. And perhaps it's true that I was tired of listening to it. What do you mean, energy? It got very, very frustrated me because as a trained scientist, I'm supposed to know what that means. Everybody agrees. It's energy. I can think of countless examples in my leisurely enjoyment of science fiction when energy is referred to as a visceral thing. Particularly, I remember an episode of Star Trek in which, by the end of an episode, the revelation was made that some alien creatures were pure energy. And that is a misuse of the term energy. But in order to understand that, I have to get the idea. I have to really understand, bare bones, what is meant by the term energy. Early in the 1960s at Caltech, the famous physicist Richard Feynman gave a wonderful series of lectures intended for undergraduates in physics. And in that lecture series, he explained energy in the context of a little story that he told. And that it was in that story told by Richard Feynman that I first came to understand the true meaning of what is energy. And that understanding has informed my science every time I encounter the term energy in every context. So I think it's essential for every student of science to hear this story and to see how it translates into a deep and subtle understanding of the concept of energy. Here's the thing. I'm about to tell you a story. The story has many features. It's important to appreciate as you hear this for the first time that a great deal of care has been taken in choosing exactly how to tell the story and the details of it. In the end, there'll be a little bit of a reveal. But as we go along, just try to appreciate the facts of the story and not try to think too deeply into it or try to figure it out. Simply take everything on face value and we'll interpret it at the end. Somewhere in the world there exists a room. And there's a little boy who every day is brought by his parent to the room to spend the day while the parent goes away. It's really important that the boy is inside the room all day unobserved. This room is very, very plain. We see here it has a door and a window. One door for perhaps people to enter and exit, and one window through which the light shines, the wind blows, and so forth. And also it has inside a box with a lid that can be closed so that the contents of the box cannot be seen. There's also a basin that's full of water. And the thing about this water is it is filthy dirty. So dark is this water that you can't see through the water and you wouldn't dare reach your hand into it. So here the child sits, and the child has 10 blocks to play with throughout the course of the day. The 10 blocks, I need to be a little bit specific about them. The 10 blocks are absolutely identical in every measurable way. They have the same mass, they have the same physical dimensions, they're the same color. And it's necessary for the story, but not necessary for the science. But for the moment, I want you to consider that the blocks are indestructible. There's nothing that the boy can do to physically change the blocks in any way. For example, the boy cannot light the box with blocks on fire and have them disintegrate or anything like that. And certainly there's not going to be anything magical going on. So here this boy sits in the room with the blocks and the box and the basin. There's a door and a window. Very often when we do science, we talk about systems, and whole books have been written about the nature of systems. What is really meant by a system is it's an intellectual idea. A system is a group of objects that you identify, that you choose to consider together, even if there are interactions between those individual objects. So here, my system is the child, the blocks, the box, and the basin. And that is the contents of the room. And so the walls of the rooms define my system. Everything that is inside the room is part of the system, and everything that is outside of the room is part of the surrounding environment. So the walls of the room are what we term the system boundary. Everything inside is in the system, everything outside is outside the system. And so, in the morning, the parent brings the boy to the room and leaves, closing the door behind, and the boy is unobserved. When the parent comes in the first time with the boy, the parent counts the blocks. There are 10 blocks in the room. Now, because the blocks are indestructible and the parent knows this, it's a reasonable expectation for the parent to have that when they return at the end of the day, they will observe that there are still 10 blocks in the room. Except that one day, the parent comes back and discovers that there are 9 blocks in the room. One of the blocks has mysteriously disappeared. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, wait a second. No, I see. Do you see over between the box and the basin, there's a block wedged down between there? What's happened during the day is the boy is playing with the box and moves the blocks around, and one of them got wedged down in between there. The point is this: if you're interested in keeping track of the number of blocks that are in the room, sometimes you have to be really careful because the blocks can be difficult to observe. So it takes some sort of care in measurement to do that. And so the parent reaches down in there and pulls the block out, gets them all back together, and then there are 10 blocks, which, as you said, is the reasonable expectation. If any blocks are missing, it's a good idea to look around carefully and make sure that you've counted properly. So the days go by and the parent comes counting 10 blocks every time. But then, one day the parent comes in and finds that there are only 7 blocks visible. Now the parent has some experience in making sure to count the blocks carefully. So all the little hidden places that the blocks could possibly be or have been found in the past, the parent looks in all of those locations and there are only 7 blocks in the room. Well, a little bit more careful investigation, we realize what happens. The parent looks out the window and sees that there are 3 blocks outside the window on the grass outside. So what has happened is that 3 of the blocks have crossed the system boundary. 3 blocks have actually left the system. Now, we didn't see it happen, but probably what you're thinking is at some point during the day, the boy decided to chuck some blocks out the window. So that's an idea that you have about why blocks have gone across the system boundary, despite the fact that you didn't actually see it. It's a reasonable and logical conclusion to come to. So the parent goes outside and collects those blocks and brings them back in again, because as the days go by, the parent becomes more and more concerned that there should be 10 blocks. And indeed, once the 3 are brought in from outside, we once again have 10 blocks in the room, and all is right with the world. It's a wonderful thing about nature, that it can be surprising. Counting 10 blocks day after day, the parent comes back at the end of a particular day, and there are 15 blocks in the room. 15 blocks. The absence of blocks was something that we were able to sort of intellectually accept. We might not have counted properly, or now we discover blocks can go out the window. But now there are 15 blocks. Well, some further investigation goes on, and the parent realizes that 5 of the blocks that are in the room aren't blue, but are in fact purple, perhaps. And a little bit of questioning reveals that during the day, the boy's friend Susie came by, and Susie has blocks. So she brought blocks in through the door with her, and she left those blocks in the room with the child. So now we got excess blocks because blocks came in through the door. So if we're interested in counting a certain number of blocks and always getting the number 10, we have a difficulty with blocks crossing the system boundary, either exiting or entering the system from the environment. Well, if we're careful, it's possible that we could devise a scenario where we can prevent that from happening. In our story, there's a simple solution. We're simply going to get a big board and nail it across the door so that nobody can enter or exit through the door. That way, nobody can come in bringing blocks. We also take a board and we cover up the window so that the boy can't throw the blocks out the window, and we make it impossible for blocks to cross the system boundary. No blocks can come in and no blocks can get out. Now we call this an isolated system. An isolated system is one that cannot interact with its boundary. And so in this case, the isolated system is the room, and no blocks can get in or out. If no blocks can get in or out of the room, then this room is an isolated system. Now we can be absolutely assured that when we count up the number of blocks at the end of each day, there will be 10 blocks, because the number of blocks cannot be exchanged with the environment surrounding the system. 10 blocks at the end of every day. Well, now I see another problem develop. At the end of the day, a parent comes in and counts that there are 7 blocks. Being careful to count according to all of the techniques that have been devised for making sure the count is accurate, realizing that the door is barred and the window is blocked. There are only 7 blocks, and the parent realizes, well, hang on a second. Perhaps the blocks are inside the box here. So the parent goes over to the box intending to look, but the boy jumps up on top of the box, says, no, you can't look in the box. You're not allowed to. I won't let you. Throws a tantrum. The parent says, okay, fine. The parent doesn't mind because the parent is quite clever. What the parent will do is wait until a time when all 10 blocks are visible, and then weigh the box. Once the parent knows the weight of the box, when this situation arises again, and there are 3 blocks missing, the parent can do something rather clever to verify whether or not the blocks are inside the box. With only 7 blocks apparently present, 3 blocks missing, the parent can once again weigh the toy box, getting its weight, W, subtracting from that the initial weight of the box, that is, the weight of the box when 10 blocks are present. You find that the weights are not the same. The difference in the weight divided by the weight of a single block is approximately equal to the integer number 3. I say approximately because measuring the weight of the box and measuring the weight of an individual block has an uncertainty in that measurement. So we wouldn't get exactly 3 as the answer. We'd get 3 and some decimal. What we would discover, though, in the course of doing this experiment, is a little aside about measurement and science and experiments. What we would discover is that if we found some way to improve this technique, for example, simply finding a better way to measure the weights of the box and the blocks, then we would find that the number would get closer to 3, never further from 3. So improving the experiment only brings the number closer to 3. The conclusion that we draw from this experiment is that the 3 blocks are inside the box. This is a really, really important point. We have not actually seen that the blocks are inside the box. So are they? Well, the fact is, the blocks being inside the box is the most reasonable interpretation of this data. And our experience in science tells us that the most reasonable conclusion is probably the correct one. Is it possible that someone could see this demonstration and explanation and say, oh, well, it could be something else that happened? Well, yeah, but what we would discover is that that other idea, that alternative possibility, would generally be more complicated than this one. And so we satisfy ourselves that the three missing blocks are actually hidden inside the toy box. Here we have a new problem. We come in at the end of the day and we observe that there are only 5 blocks present. Well, we know what to do in this case. We'll go ahead and weigh the toy box. The trouble is we find that the toy box weighs the same as the unladen toy box. And so our conclusion is that there are 0 blocks inside the toy box. 5 are missing. I wonder if you noticed as the slides made their transition, the level of the water inside the basin has risen, which is an interesting sort of observation to make. And I suspect that there might be something going on with that. The parent is quite clever. So what the parent's going to do is wait for a time when all of the blocks are accounted for and measure the depth of the water. The reason why is that if I measure the depth of the water and also the cross-sectional area of the basin, I can calculate the volume of water in the basin. And just like using the weight of the toy box, this gives me a way to leverage the number of blocks that might be hidden inside the water. So 5 blocks are visible. Here's the calculation. We take the volume of the water in the basin when we suspect that some blocks are potentially hidden there, and we subtract the volume of water in the basin when all 10 blocks are accounted for, and we find that there is a difference. If we divide that difference by the volume of a single block, we find the answer is approximately equal to 5. Again, that's an experimental result, so it's subject to experimental uncertainty. But in the same way, if I improve the experimental technique, I just get closer and closer to 5. So what we presume from that is that the 5 blocks are actually hidden inside of the water. Remember, the water is dark and dirty. We can't see, and we wouldn't want to feel around inside. So the blocks are in the water, we presume, but we have not actually seen them. And you might say, well, yes, but obviously that is the only rational conclusion that I can come to based on the experimental evidence. Well, that's good. You're doing science. And again, someone might come up with some more elaborate explanation, but our experience shows us that elaborate explanations turn out to be false in favor of a simple nature. It's time to take our thinking about this situation to a higher level. Imagine that this is the situation. We come in at the end of the day and we discover that there are no blocks visible. But now we have the tools we need to do a very quick calculation and figure things out. We measure the weight of the toy box and we do our little calculation. We measure the depth of the water in the basin. We do our little calculation. And we get a result that at this point in the story is no great surprise at all. Suppose we do our box calculation and we find that the result of that calculation is approximately 2. And we do the basin calculation and we find that that result is approximately equal to 8. We're not surprised at all because the total of those calculations would be equal to 10. I want to propose now that this is always the case. Every time we come in at the end of the day, there are no blocks visible whatsoever. And so then we do this calculation. On any given day, the distribution of the blocks might be different. I might come in on one day and find 3 in the box and 7 in the basin. I might come in and find none in the box and all 10 in the basement, or any combination. But it would always add up to be equal to 10. And that idea doesn't surprise you at all because we have gone through this exercise of talking about where the blocks are and how they're discovered. But imagine now that this was always the case, that we had never seen any of the blocks. Imagine that this happened just because we had an interest in the weight of boxes and the depth of water, and we had done a lot more investigation. Just figuring it out from the missing blocks in the room was easy to do because we had a reasonable suspicion about where the blocks were going. But to figure it out without ever having seen any of the blocks before would be a significant trick. It would take a lot of experimentation. It would take a lot of flawed hypotheses that would be refuted. And then ultimately we'd make this realization that whenever you calculate the weight of the box and do this calculation, and you do the depth of the water, and you do this calculation, it always works out to 10 every time. That is a very, very mysterious thing if we had never seen blocks before. And if someone came to us and said, what's going on here? Well, we would say, well, you see, you calculate this number, and you calculate this number, and you add them together, it always is equal to 10. Well, that's very fancy. Do you have a name for that? Sure. We call that energy. Do you see? The box has a certain amount of energy, and the basin has a certain amount of energy, and the total amount of energy is this number that I calculated. And a person might question me about that and say, well, wait a second. It's very strange, isn't it? Because when you measure the weight of the box, you're measuring the box's mass, technically, because the weight of a thing is the mass of a thing multiplied by the acceleration due to gravity. So that calculation is based on mass. And when you measure the volume of the basin, you're using a meter stick, and so you're measuring length. That measurement is based on space. So these two measurements that are giving you these numbers are based on completely disparate, fully independent physical quantities of the universe. And yet they add up to be a number that's significant. That's a remarkable thing. Not only that, you tell me that as you check time after time, coming back at the end of the day and doing the calculation to ascertain the number of blocks in this location or that location changes, but the total is always 10. So there's time dependence to this energy phenomenon. It's quite stunning, to which there's no particularly good answer for that, except that this is the way the mechanism of the thing works. Now, the very next question that our casual outside observer is going to have is, what is energy? Now remember, we've never ever seen a block. So we don't know this number that we're calculating is a number of blocks that are hidden. So what is energy? Now, we might say, it's almost as if there are hidden blocks. We might be really clever and have this sort of fantastical idea that maybe blocks exist. But we've never actually seen one. And there's uncertainty, the measurement, so there's no exactness to it. So talking about the existence of blocks is some nonsense. The only thing that we can really say is that the energy is a number that we can calculate that has the remarkable property that its total remains the same no matter what occurs. And the occurrence here being the number shifting back and forth between the box and the basin. All we can say is that a number that can be calculated. It's a kind of sameness that this system has that we've identified through careful experiment and a lot of work. Speaking of work, it turns out that while the box contains a certain number of blocks, let's say energy, the box contains energy and the basin contains energy, the energy switches between the two. So if I want to push this allegory to the point of analogy, the box is kinetic energy, the energy of motion. The basin is potential energy, the energy of position. And when the energy is moved from box to basin and from basin to box, we know that while our back is turned, the child is the one doing the shuffling. When we're not watching, the child moves blocks from one to the other. We never see the blocks, but the child moves them. The child is conservative work. The child shifts the energy around inside of the system, but the action of the child always conserves the number of blocks. The action of the child conserves the energy of the system. Throwing energy out the window is non-conservative work, because when I throw the blocks out the window, the number of blocks in the room changes, actually decreases. Bringing blocks in from the outside is also non-conservative work that increases the number of blocks. So in the end, what we've discovered here is a sort of law of conservation of blocks that is analogous to the law of conservation of energy. Just like we imagine that we have never ever seen a block, we've never ever seen energy. Energy is not a thing that you can hold in your hand, or a glowing blue shimmer like you might see in a sci-fi film. The reality is that energy is a number that we can calculate that has the remarkable property that it never changes or changes predictably no matter what occurs. That is what energy is. I think that some might say that's an unsatisfying answer, but it's the answer that's true and that applies in all areas of science, biology, chemistry, and physics. Every time the terminology energy is used, this is what it means. Now, it turns out that knowing how much energy is here or there in a system makes it possible for me to interpret the behavior of the system. Having a large number of blocks in the toy box is a large amount of kinetic energy, which is a large velocity. And it turns out there are certain rules into how the energy can be exchanged between the two. And finding out those rules is sort of part and parcel of doing our modern science in every aspect, on every level. As always, with these sort of revelations about the nature of things in our universe, you might come to ask, why is it this way? Well, that's what physics and ultimately all sciences are about. We don't really understand the truth of things. We observe the universe and we come to understand the rules. And then when we're done all of our labors and our work and our science, then we sit back for a moment and we contemplate the nature of things and the great mystery. We speculate about what might be beyond.